Hi, everyone. I claim that this here is the equation of an ellipse. Let's put this in standard form and analyze the ellipse. Graph 9x squared plus 4y squared. And by the way, one hint that it might be an ellipse is that we have an x squared term and a y squared term in here. They're on the same side and the coefficients are the same signs, but they're not equal. If they were equal, we'd be more likely to have a circle. All right, 9x squared plus 4y squared minus 54x plus 40y plus 37 equals 0. So x squared and y squared are the highest powers of x and y in this equation. Find the center, vertices, foci, and E. I wouldn't have you actually graph on an exam, but in principle, if you have all this information, you should be able to. Now, our first step to get to standard form, remember standard form is going to look like one of these guys, right? First, we're going to group the terms. We're going to group the stuff in X and the stuff in Y. So we group the X squared term and the X term over here, the Y squared term and the Y term over here, separate with a plus sign. And then we subtract 37 from both sides. So I'm grouping these two, and then I'm subtracting 37 from both sides. So the non-zero constant is on the right side. Okay, so group in X and X squared, group in Y and Y squared, non-zero constant over here. And don't forget that right side, by the way. And then for each of these groups, we factor out the leading coefficient. Now, even if this were like a negative 55, or if this were like a plus 39 or plus 41, even if we end up with fractions inside here, you always factor out the leading coefficients. You have no choice. So here, you factor out a 9 from this group, even if that leaves an ugly fraction in here. And from here, you factor out a 4. Again, even if that leaves an ugly fraction in here. In this case, we don't leave ugly fractions. We have 9 times the quantity, x squared minus 6x. It turns out we complete the square with a plus 9. Then we have plus 4 times the quantity, y squared plus 10y. It turns out we complete the square with a plus 25. Equals negative 37. And then we'll discuss these later on. Now over here, to complete the square, remember we take the coefficient on x, here it's negative 6. We take half of that, we get negative 3. The sign doesn't even matter because we're going to square at the end anyway. But half of negative 6 is negative 3. When you square negative 3, you get positive 9. There's always a plus sign in here. Likewise, in here, we take the linear coefficient. The coefficient on y is 10. Half of 10 is 5. The square of 5 is 25. So we insert a plus 25 over here. But we can't just put in numbers because we feel like it. We have to pay for them. In this case here, we're going to balance things out. We're going to pay for these insertions over here by making adjustments on the right side. So now, if we insert a plus 9 inside here, are we really just adding 9 to the left-hand side? Well, the thing is, look at the 9 out here. When we insert a plus 9 inside the parentheses here, we're actually adding not just 9, but 9 times 9 by the distributive property. So that's why when we insert a 9 in here, we're adding not just 9, but 9 times 9, or 81. That's why I put plus 9 times 9, or you could put plus 81 over here. Likewise, over here, I'll put this in green, let's say. Let's put in green. Okay, the plus 25. When we insert the plus 25 in here, are we really just adding 25 to the left side? No, because there's a 4 out here, right? When we insert the plus 25, the 4 distributes in and hits the 25. So when you're inserting a plus 25 in this group, you're actually adding 100 because you're actually adding 4 times 25 to the left-hand side. Therefore, let's add 4 times 25, or 100, to the right-hand side. So because of this, we add 4 times 25, or 100, to the right side as well, because we've done that on the left by inserting a plus 25 in here. We're compensating. If we're adding 81 and adding 100 to the left side, we better add 81 and add 100 to the right side. Now factor these as factor, because bear in mind, when we apply CTS, we're developing these as PSTs. We're creating perfect square trinomials. Perfect square trinomial over here inside parentheses. Also, perfect square trinomial over here in parentheses. Now factor the PSTs, the perfect square trinomials, as squares of binomials. Over here, we have 9 times. Factor this, x squared minus 6x plus 9. That's the square of what? Likewise over here, 4 times the quantity, y squared plus 10y plus 25. This trinomial here, this perfect square trinomial, factors as the square of what? You can also simplify the right side. I'll give you a few moments. Factor, factor, simplify on the right. All right. X squared minus 6x plus 9 is a PST, factors as a square of x minus 3. You take this sign in here, the middle sign, and the square root of that. Basically, this should look familiar. It's the middle guy in the whole completing the square process. It's the negative 3 here. Plus 4 times, okay, this is the square of y plus 5. A key hint, half of 10 is 5, or the square root of 25 is 5. You take the plus sign in the middle over here. Equals negative 37 plus 81 plus 100 is 144. But wait, what do we need on the right-hand side? It's almost like matrices. What do we need on the right-hand side? We need a 1 on the right-hand side. How can I accomplish that? By dividing both sides by 144. Divide the left side by 144, that is each term. Divide the right side by 144, we end up with 1 on the right side. All right, when you multiply by 9 over 144, you're dividing by 144 over 9. Similarly, when you multiply by 4 over 144, you're dividing by 144 over 4. The only reason why I'm doing this is just in case you get uglier numbers down here. You could end up with fractions here. Like, for example, if that's a 145, you'd have 145 over 9 down here. Fortunately, these do simplify to integers. In fact, you could have gone directly like so. Right. Okay, 144 divided by 9. Okay, 9 divided by 9 is 1. 144 divided by 9 is 16. Over here, 4 divided by 4 is 1. 144 divided by 4 is 36. So we're lucky. We do end up with integers down below. But we could have had fractions. That's why I did this. Of course, you don't have to do this on the homework, unless you actually do get fractions down there in the end. Okay, equals 1. Don't forget the equals 1. Again, this middle line here is not wrong. It's just that you might want to go straight from here to here. But if we had a 145 there, you would need this. All right. So we're done with standard form. This is in standard form for the equation of an ellipse. All right, where's the center of the ellipse? Quick, where's the center of this ellipse? A nice trick, which also works for circles. What point, what values for x and y, what ordered pair will make the left side equal to 0? That's a nice trick. Positive 3, negative 5. What makes the left side equal to 0? X equals 3, y equals negative 5. Another way of looking at that, the top here, okay, you look at the x minus 3 is of the form x minus h all squared, where h is 3. X minus 3 is of the form x minus h, where h is 3. Likewise, y plus 5, that's what all squared? Okay, so y minus h all squared. The square of y plus 5 is the square of y minus what? Well, when you add 5, you're subtracting negative 5. When you add 5, you're subtracting negative 5. K is negative 5. But the easy way to look at it, what makes the left side equal to 0? All right, 3 comma negative 5. Cast of characters. Take a look here. Which denominator is bigger? Is it the denominator in the x fraction or the denominator in the y fraction? It's the denominator in the y fraction. So because the 36 is our a squared, is the larger denominator, we have a squared equals 36, which means a is what? A is plus or minus 6, but by definition, a is positive, so we zap that symbol. A is 6. And this indicates, now because that a squared is the larger denominator, that means that we have a y long or vertical ellipse. We have a y long or vertical ellipse because the denominator here is bigger. A squared is 6, therefore a is 6. Over here, this is a smaller denominator, but we can still use it, right? B squared is 16. What's B? B equals plus or minus the square root of 16, or 4. But remember, by definition, A, B, C, and E, for that matter, are all positive. All right? A, B, C, and E are all positive. We zap the plus minus. Of course, H and K themselves can be negative, the coordinates of the center. But A, B, C, and E, they're all going to be positive. All right, again, we have a squared equals 36 under the y square stuff, so it's y long. Right? A is 6, b squared equals 16, therefore b is 4. Find c. Remember that handy formula. C squared equals a squared minus b squared. A squared is 36, b squared is 16. We actually do need these things over here. C squared is 20, therefore c equals plus or minus the square root of 20, but we zap the plus minus, right? We originally started the plus minus, but then we zap it. Z is by definition positive. The square root of 20 simplifies to 2 root 5, right? 4 divides 20 nicely. 4 is a nice perfect square, comes out as a 2. Root 20 is root 4 times root 5, or 2 root 5. All right, observe that this is less than A. This is about 2 times 2.2, which is about 4.4. That's still less than A. Right. Find the eccentricity, C over A. C is 2 root 5, A is 6. Simplify, we get root 5 over 3. If you round that off, that's about 0.745. So fairly elongated. Not too elongated, but fairly elongated. Right. So we sketch the graph. Again, I wouldn't do this to you on a final exam, but you should know the anatomy of this. You should know what points are involved here and these various parameters. All right. Again, for good show, let's graph this on Desmos. 9x squared plus 4y squared. Let's see if we can do it. 9x squared plus 4y squared minus 54x plus 40y plus 37 equals 0. How do you like that? Desmos does it. Sounds like a campaign ad. Desmos does it. The center is at, what was it? It was at 3, -5. All right, looks good. All right. Oh, it's a y long ellipse, vertical y long ellipse, because the bigger denominator was under the y stuff. All right. We have all this information. Okay. Now, from the center, how do we get the vertices? Well, it's a y long ellipse, so the vertices lie above and below the center. Okay. It's a y long ellipse. So the major axis is vertical and contains these 5 key points: the center, the 2 foci, and the vertices. The center is at 3, -5. The vertices are 6 units away. A equals 6. Okay, that affects the vertices. Okay, that means that from the center we walk up 6 units to get one vertex. We walk down 6 units to get the other vertex. Now, the center is 3, -5. Which coordinate stays the same on this vertical major axis? The x-coordinate stays the same, x equals 3. It's the y-coordinate that's changing. It's kind of like the frame method for trig functions. If you take y equals -5 and you add 6, you get +1. If you take y equals -5, if you subtract 6, you get -11. It's a lot like the frame method for y-coordinates in trig. Let's plot these points, 3, 1, and 3, -11. Good. And 3, -11. Good. This is all very comforting. We have the center right now and the 2 vertices. Now for the 2 foci, it's similar to calculating where the 2 vertices are, except that when we change the y-coordinate, we don't add A, we add C, right? That's the distance from the center to each focus. We add C to the y-coordinate, we subtract C from the y-coordinate. So the coordinates of the foci go 3. All this is happening on the vertical line x equals 3. Here's the vertical line x equals 3, right? That's the axis, the major axis. The major axis lies on there. Okay, and these are the y-coordinates. All right, so 3, -5 plus 3, -5 plus 2 times square root of 5. That's up there. And 3, -5 minus 2 times the square root of 5. That's the blue point down there. These are the 2 foci. If you want to draw this ellipse, get a taut string of length 2a, as it turns out, the major axis. I'll show you that. Okay, put thumbtacks at the edges, and you can sweep out this ellipse if you keep the string taut. All right. The eccentricity is about 0.745. It's fairly elongated, as you see here. Wow, that's a lot of information. Oh, label here, right? So again, these 5 key points: the center, the 2 foci, and the 2 vertices on this major axis of this y-long or vertical ellipse. It's like the mall in Washington, D.C. And then if you wanted the endpoints of the minor axis, all right, you would take the center and you change the x-coordinate. You would change it by 4. So you add 4, 3 plus 4 is 7 over here, 3 minus 4 is -1 over here. So -1, -5, and 7, -5. Again, if you take the center, -7, -5. Okay. There you go. Okay. Again, to get those points, we share the y-coordinate this time. They're on the horizontal line y equals -5. These points share the same y-coordinate. The x-coordinate changes. From the center, 3, you add 4 to get the 7 here, subtract 4 to get the -1. 4 was B, the semi-minor axis. By the way, this A is called the semi-major axis. B is called the semi-minor axis. All right. Next time, what explains the formula for C that we used up here? Next time.